All right, line V1, learn task 9. We're going to take a look at a lot of the components, or what they refer to as the features, that we are going to go and have of a synchronous motor starter. We're going to go through the actual operation of them in the next learning task. Learning task number 10 is all to do with, how the stuff is going to go and happen. Right now, we're just going to go and take a look at what these components themselves are. And it's going to be a number of brand new ones that we haven't dealt with before, but they're really not that complicated. So we'll take a look at them later on. First thing that we're going to talk about is just what the synchronous motor is. Once again, we're going through, the motors, and then we're going directly through the controls right after that. But we know that a synchronous motor is a motor that is designed to go and start as a regular squirrel cage induction motor. Once we get that thing all the way close to speed, we then go and apply power to the rotor. And the rotor has got a DC field on it. And when we apply power to that rotor, then it is going to go and lock in. So it can operate at the actual synchronous speed, which is really, really useful if we've got loads that we cannot go and have changing. The other really, really useful thing about the synchronous motor is we can use them as a variable capacitor, completely 100% variable by over-exciting or under-exciting that field. So we've got a bunch of different components that are then going to be, utilized in, or a bunch of different components used to control this so that we can accomplish those two things. Looking at our diagram that we have over here, we're going to go through these things, kind of one at a time. I want to start with my safeties that I'm going to go and have. First of all, this is going to go and be a motor, which means that that motor could get operated with, way, way, way too much load off of it, which means that we could burn it out. So we have always got overload heaters inside of here. These things are designed to react to the amount of current that's going through them. They create heat, and when they create heat, they then go and trip out the set of contacts, or overload relay. That's standard for all squirrel cage motors, all synchronous, all wound rotor motor. I mean, it's just an overload happens on a motor. It's responsive to motor current. The other thing that we see in line with it over here, and this is kind of cool, is that we have got a second safety here that is going to be called the out of step. And what the out of step is going to go and do is it is just going to go and monitor for however long that we, are starting up on this motor. We want to make sure that we are not starting too long. So it is just going to go and energize this out-of-step relay anytime that we are operating at less than our rated amount of speed. When we're not operating asynchronous, if we are out of speed for too long, it's going to go and open, which would go and drop this whole thing out. And the big reason for that is that, we have got that amortisseur winding. Remember, it's a squirrel cage winding that exists on the rotor over there that is designed for intermittent duty, for starting the motor and just to go and help it, pick up if it's dropped out of lost synchronization, etc. We don't want to be running it off of that full time. So we have to be very careful, make sure we've got that out of step relay that we're going to have inside there. That's going to be our second safety that we're going to have inside there. Outside of that, pretty much everything else is going to go and be the same for my regular startup. If I take a look at components, I see that inside of here, it's going to be a regular start-stop type of component, other than I've got the addition of another relay that's going to be inside of here, which is going to be my CR1 contact relay 1, which we see is going to go and give me a contact inside of here. This is just a control relay that we have, not an actual contactor. In some cases, we'll use a small relay that then we use to fire the coil of a contactor. Very large motors will have very large contactors that are going to be up in, 5, 10, 8 amps. It's not going to be unusual for the coil if it's a massive, massive motor with a massive, massive contactor off of it. So it's just going to be a little control relay for that. As far as the actual location of our out-of-step relay, our out-of-step relay is shown a little bit different than the way that we're used to seeing relays inside of here. We determined that this thing is a safety and that it is going to go and be designed, that this thing is supposed to go and be energized. The out-of-step relay is actually shown inside of the DC over here as being a zigzaggy line, which is not our usual way that we go and draw these. It's a little bit like one of these, an overload over here that's responsive to motor. This is going to be the same type of thing where it's going to be resistive more than anything. We use it as a relay. It's got a set of contacts that's attached to it. But it is going to go and monitor the amount of time that we have got current going through this pathway. Because there is going to be a pathway that we place inside of here that is going to be based upon the field itself being shorted out. I want you to just take a look at this pathway over here. We're going to establish it. if I take a look at this path over here, going down and up through here, we see that there's a continuous path of current that's going to be able to go through our field winding itself, that we're going to go and apply this because we see that there's going to be a discharge resistor that we're going to go and have in here as well. This path is here as a safety because we know that at the instant that we start up this motor, we're going to have that synchronous field around the outside. This rotor is going to be at 0 RPM, and as a result, we are going to go and get a very large amount of voltage. EG is equal to K phi N. We're going to get a large amount of voltage that would be induced in this winding over here. You can use BLV, whichever one you prefer to work off of. We would see a large amount of voltage that would be induced inside of this DC winding. And if we have got an open set of windings, if all we had was this over here, what we would get is we would get this problem where we are going to go and have an inductive kick. We're going to have this collapsing field that would go and have, that would happen continuously. We don't want to go and have that, so instead we want to go and provide a continuous path. That's this blue path that is going to go and allow us to dissipate any induced values of voltage, and we're just going to dissipate them as heat over top of this discharge resistor. Anytime that the discharge resistor is going to be placed in line with my field, which is going to be while I'm trying to accelerate the motor itself, I'm going to also be passing current through the out-of-step relay, which is going to go and just be, once again, a small heater. This thing is designed to go and produce a little bit of heat, just like an overload, and if it produces heat for too long, it is then going to go and kick this out, telling us that we've been accelerating for far too long. Field contactor is in line with that. So let me just erase these over here. Let's go and take a look at the actual field contactor. The field contactor coil is all the way over here, and we see that's got a number of associated contacts with it. We have got normally open contacts over there, and we are going to go and have normally closed contacts over here. This is going to be a specialized type of contactor that is going to go and make sure that we have got overlap or positive overlap on my contacts before I go and drop out this field resistor path over here. I would want to make sure I've got DC that is going to go and be applied. So these are going to operate first before these ones are going to go and operate. Really, if I were to go and take a look at the timing of these, I would see that the normally open ones would close in. They would go high slightly before the normally closed ones would go low. Here's my NC, here's my NO that I would go and have. And I would also see that on the other end, if this thing is going to go and fall out, this one is going to go and close in a slight bit before these ones would go and fall out. And really, this type of overlap is here as a safety. These are very small. I mean, we're talking like milliseconds of difference that we're going to go and see across here. But it's going to be very important that this normally closed is always going to be the last one out and the first one back in when it comes to any timing, because that way we are always guaranteed to go and have a path through that discharge resistor. This contactor is going to get applied through a number of other stuff that components that we're going to go and take a look at. The biggest one of these is going to go and be what we refer to as our PFR, Polarized Field Relay. Polarized Field Relay is going to be a special type of relay that is going to go and work off of my reluctance. And reluctance is just another one of our magnetic terms that we should be familiar with. It's just going to be the opposition to setting up lines of magnetic force. A couple of ways we can set up we can oppose, create reluctance. One of them would be just having a hard type of material that doesn't want to rearrange the magnetic domains. The other way would be to be holding those magnetic domains. It's like having, either a door that's hard to open because the hinges are stiff or because somebody is holding that door on the opposite side. What we have is we are going to go and play with the domains inside of a polarized field relay. And the more domains that we lock down, the fewer domains that we are going to have left to go and play with. Let's go and take a look at me polarizing a couple of domains. Okay, we're going to go and represent domains right now with just these lines that we are going to go and see over here. I'm going to go and start. I'm not even going to look at theirs right now. I'm going to just say that I have got a north over here. I've got a south over here because this is DC. And I would be able to go and establish, off of my currents when I've got a north and a south. If I've got current traveling through there in that direction, I would have a north off of this. If I establish a DC field, what I'm going to get is I'm going to go and get these domains that are going to align with my DC magnetic fields. Okay, I'm just going to go and draw these all out as red arrowheads over here. I'm going to get some that are going to go through like this, and this is really the circuit I'm going to look at. I'm not going to bother with all of this stuff yet. We'll deal with that in a second. What this does is this is going to go and have domains that are locked down. Now, how many domains are going to be inside of here? Well, I don't know, but it's going to be a physical amount because we're looking at a physical material. So let's say that based upon the number of total amount of magnetic lines of flux that we have inside of here, that I have got half of my domains that are going to be locked down. That means I've got another half of my domains that are going to go and be able to be switched around, and they're going to be able to be switched around in any direction. Really the critical one is going to be this direction over here. If I've got half of these locked down, then I'm going to go and not be able to go and utilize them. These red ones here are locked down. So my AC is going to go and alternate inside of here as well. And my AC wants to go and align its coils, or align its magnetic lines of flux. If my AC is going through in a direction that would be aiding the DC over here, my AC could be creating lines of flux that are going to go up and through like this, back like that, as well as it could be going through like this, right? We've got 50% of our domains that we have not locked down. So if my AC is going through in one direction, I'm going to be able to go and have all of these domains like this, which means that right over here, magnetic lines of flux are really going to want to travel through this because we see that all of those domains are aligned. It makes it easier for it. Lowers the reluctance, increases the permeability. However, when my AC changes, and remember that AC is an alternating current, so it's going to go and change its direction of current through the coil, which if you know your left-hand rules means that all of these are going to have to go and change as well. And so what I get is I get that my AC is now going to flip over here, and it's going to go and try to arrange. It's going to have, these ones over here that it can easily access, but it's going to have a really, really hard time forcing back against that DC that is going through here. We see that it's in opposition to the DC all the time, which means that really we have lowered the amount of permeability on one of my coils. Now, the more DC current that I go and put through here, the more domains that I'm going to lock down. I can completely lock down these ones here to the point, if I would drive it to saturation, that my AC would not be allowed to go and change any of those domains over there, which would mean it'd be really, really hard for my AC to create a magnetic field, which would mean that it would not be able to go and attract this little bar that we are going to go and have over here. This is going to allow us to basically change the sensitivity, hair trigger this thing so that we can adjust when this thing is going to magnetize or not. The amount of DC that I run through here is going to go and adjust the amount of AC utilization of the rest of the coil. Very little DC being put through there, lots of room for me to go and play around with the AC. Very loud, lots of my DC that's going to be inside of here. Then I'm going to go and, I don't know, it all just disappeared over there. But what I was saying right before I completely lost this thing here once again, was that anytime that I stick lots and lots of current through here, I'm going to have lots of my core that is going to go and be unavailable. If I stick a little bit of DC current through, I'm going to have a little bit of core that's going to be used up, but most of it's going to be available for my AC fields. And the more that I leave for my AC, the more that's going to be able to go and react to any sort of AC that I'm going to have. This AC, by the way, is going to be picked up from my field. This is going to be off of that field coil that we are going to go and pick this up. And if I take a look at where the field is, I see that the field is on my rotor. So what I know off of that is that this is going to have a high frequency at the instant of startup. We're going to go and have a high frequency in voltage, but then it's going to go and attenuate and get smaller, right? Go back to what we covered off of the wound rotor motor, off the wound rotor motor there 2 days ago or yesterday. You would see that we have got this frequency that's going to be induced inside of a rotor. We get the exact same frequency that's going to be induced in this, which means that at the instant of startup, I'm going to go and have maximum AC, and then I'm going to be losing AC. This little arm that we see over here is going to go and be spring operated. There's going to be some sort of spring tension that's going to be trying to pull this thing back out over here. And we see that this arm is also going to go and have a set of contacts that's going to be placed on it. That's what they're trying to show over here with that arrowhead, is that we've got this set of contacts over here. Right now, if I can go and generate enough AC, I can go and hold this like that because my magnetic lines are elastic. My magnetic lines are going to go through here and they're going to use their elasticity to go and pull this bar against that spring. But if my magnetic lines get too weak because I can't set up enough inside of there because I have fluxed out my DC over here and so I don't have a lot of AC room, what would then happen is that I wouldn't have sufficient number of rubber bands on my AC. This thing would go and pop open like that. The spring would pull it, which would mean that my contacts over here would be closed at that point. It is a tunable reactive device. It is going to just react to the amount of my field current that I'm going to go and have. And my speed. The higher the speed, once again looking at this over here, if I take a look, this is startup. This over here is going to be near operation. So once I get close to operation, I've got smaller value of voltage on my AC. I've also got a much lower value of frequency. So altogether, smaller voltage, smaller amount, or lower amount of frequency, means that I'm going to go and have a weaker magnetic field out of it. And we're going to use that weakening of the magnetic field, because initially it's going to start out closed like this. Then I'm going to go and start to lose those ones, and then this thing's going to be able to pop open, which would mean that I'm then going to be able to make some contacts off of it. It's a really, really cool little system over here. If I take a look at it, it is going to be built off of one device over here. They show this over here. I've got my AC coil. My AC coil is going to be attached to my rotor. Right? If you follow those lines through, you should see that there's going to be an attachment to the rotor. And if I were to highlight them, it's going to go and look like this. Going up and through there. We'll deal with the reactor later on. But we see that anytime that I'm during my startup, I've got a couple of components that are going to be in line. I'm going to have the AC coil that's going to be in line. I'm going to have the out-of-step relay that's going to be in line, monitoring how long I'm going to be, doing startup. And I'm going to have a discharge resistor that's going to be in line, taking care of any nasty induced voltages that are going to be coming off of that coil over there. And I'm going to go and have this set of, positive overlap contacts that's going to be closed at that point, allowing this whole current to go and operate. We will sometimes go and have a second rheostat that is going to go and be in line with this, my PFR, polarized field relay, because if I stick another rheostat in line with this, and we're not going to leave that on the front face, because if we leave that on the front face of the machine, then any one of my operators in the plant, or somebody that just walks by can be like, all right, crank that knob over there, and they would completely change when this thing would go and react, but it's oftentimes going to be buried on the inside of our controls so that I can just tune when this thing is going to go and snap in. We do have another field rheostat that's actually going to be in line for my field, and that's going to be when we are operating at the actual DC. We're going to go through the controls and the operation in the next learning task, the step-by-step of how it gets to this point. But at some point, I'm guaranteed that I'm going to go and have this. That is going to go and be happening, where I'm going to go and have DC. That is going to go and be placed like that across there, because I've closed in this field contactor and this other field contact here has opened up, and so all the rest of that would be out of play. We'll have some power that's going to be applied down here, but once again, we're not too concerned about all of that being in place. Ultimately, when we do get to this stage, we see that that field rheostat would be controlling the amount of current that would be going through here, which I can go and use to control my torque angle, which in turn is going to go and control how this thing is going to be excited, overly excited, under excited, and whether that thing is going to be a leading or a lagging power factor. Okay. Polarized field relay, just know that it's going to be something where we're going to have a saturatable core, and that saturatable core is going to go and control the amount of AC that we are going to go and have in there, and we're going to take a look at how that aids and opposes in our next learning cat task.